This is the second part of mechanics. We're looking at kinematics, so the motion of objects without any regard to forces, and we're looking at displacement time graphs and velocity time graphs. In this example, we have velocity against time, and there are various time values, t1, t2, t, which are unknown, and we're going to work those out. We have an object which is initially at rest. The velocity here is 0 meters per second. The gradient of the graph represents acceleration, so we have constant acceleration because we have a constant gradient, and then the gradient here is 0, so no more acceleration, just a constant velocity of 10 meters per second, and then we have deceleration in this region until the object comes to rest. Now, velocity is a vector. It can be positive, it can be negative, but you'll see that we only have positive values for velocity in this example, which means that we can treat distance travelled and displacement in the same way. So the area under the graph, so this triangle plus this rectangle plus this triangle, if you add the areas together, they will give you distance, or you can say that that's displacement. They will be the same. So long as the velocity is greater than or equal to 0, an object is always travelling in one direction, which is true in this example. So displacement and distance are the same. If the velocity was to become negative, then the object reverses direction, and displacement and distance are no longer the same. The initial acceleration, 2 meters per second squared, so the gradient of this line is 2. Using that, we can work out the value of t1, which is 5 seconds. So we have 5 seconds here. The total distance travelled was 400 meters. So the area of this triangle, this rectangle, and this triangle added together will give us 400. So here's the first triangle, the rectangle, the final triangle. Add them together, and we know what t1 is already. It was 5, and we can work out the value of t. The final deceleration, the gradient of this portion, of this line. So far we've worked out t1, and we know the value of t here. So this 5 plus this 15 gives us a value of 20, so we know the horizontal coordinate for this point. And the vertical coordinate is 10, that's obvious from the graph, so we know the coordinates for this point. Remember that t plus 50 is this region, and we've already calculated t. We add 50, and then we know what the coordinates for this point will be. 65, 0. And then from there we can work out the acceleration in its exact value, exact form, or a negative acceleration is the same as a positive deceleration. An alternative way of working out the value of t is to recognize that the shape given here for the graph is a trapezium. Here is the formula for the area of a trapezium, where h is this, which is 10, a plus b are these values, t there, the parallel sides which are opposite each other, and t plus 50 along here. And we know the area is 400, so we can solve this to get t is equal to 15 seconds. It's just an alternative way of solving the problem instead of thinking of it as a triangle, a rectangle, and another triangle. In this example, we can see a constant velocity for 30 seconds. So a woman travels at 5 meters per second for 30 seconds. There's your constant velocity for 30 seconds. Then we have a negative gradient, which represents slowing down, or a negative acceleration, or a positive deceleration. So if we were to write down this value in any formulae, we have to use a is equal to minus 0.2 until she comes to a stop, so the final velocity is 0. So the sketch of a velocity time graph is pretty simple. Constant velocity and then deceleration until at this point the velocity is 0. So we know that this is 30 seconds, that's given. The portion of the journey representing deceleration, we can work out the time taken for the deceleration by using this Suvat formula. So the final velocity here is 0, the initial velocity here is 5 meters per second, and the acceleration was negative. That gives us a time from here to here of 25 seconds. So the total time up to this point is 55 seconds. The total distance travelled is just the area of the rectangle plus the triangle, these two. A car accelerates at a uniform rate, so a constant acceleration of 3 meters per second squared for 4 seconds. So this is the initial part of the car's journey, a constant acceleration for 4 seconds. And then we can calculate the velocity here that it's reached after 4 seconds. It then travels at a constant velocity for 5 seconds. So this 4 plus another 5 seconds of constant velocity. Okay, so we're now up to 9 seconds. Before slowing down, so that would be it's a deceleration of 2 meters per second squared, which means the acceleration there would be minus 2 meters per second squared. There's some unknown value of time here, and we can calculate the velocity here and the time value here to complete our velocity time graph. So using Suvat formulae, we can work out the velocity at this point will be 12 meters per second, and then we can calculate the time taken for this part of the journey during its deceleration using v as 0. We know the final velocity here is 0. The initial velocity was 12 at this point. The acceleration is 2 meters per second squared, but it has to be a negative value because it's slowing down. That's a deceleration value, so we need to put in a negative for the acceleration. And then if we solve this, we know the time taken for this region, for this part of the journey, is 6 seconds. So we're already up to 9 seconds here, add another 6, 15 seconds up to this point. So we have our complete velocity time graph. Now in part 2, the distance travelled, and because the velocity is always a positive value, there's no difference between distance travelled and displacement. So they could have asked that question either way. So it's just the area of the rectangle, triangles there, we add them together, 120 meters. To practice, have a go at these questions. You can pause the video as and when. and the answers. More challenging problems, multi-stage problems using velocity time graphs and SUVAT. And the answers to these problems. The next video goes on to the derivation of the SUVAT formulae. So we can start with simple graphs and we can work out all of the SUVAT formulae.